My name is Dr. Mike Murphy. I'm an assistant professor of computer science and information systems at Coastal Carolina University. In this lecture, I will discuss memory protection, including segmentation and permission bits on page table entries. Remember that operating systems perform two functions, abstraction and arbitration. Mechanisms for accessing memory provide abstractions of the underlying memory hardware. However, operating systems must also arbitrate access to RAM by ensuring that one process cannot access memory that does not belong to it. Without this arbitration, a process could change memory belonging to another process, or worse, it could crash the system by changing memory that belongs to the kernel. On systems that utilize simple memory management, such as power of two methods, memory access protections are provided by a mechanism called segmentation. On the majority of modern systems which employ paging, memory protection is implemented as part of the paging system, and memory access permissions are stored in the page table. On any system, process memory is divided into logical pieces or segments at compile time. These segments include the text segment, a region for global variables, a stack region for automatic variables, and a heap for dynamically allocated data structures. Access permissions apply to each segment. In particular, the text segment is set to be read-only. Outside a single process, there must be a mechanism to track which segments of memory belong to which processes. When a process is executing, its segments are marked valid so that it can access the corresponding memory locations. Segments of memory belonging to other processes are marked invalid, and any attempt to access those segments results in a fault or interrupt called a segmentation fault. Typically, a segmentation fault causes the process to be terminated. Segment memory permissions are implemented on non-paging systems using a segment table. The segment table has permission bits that can be applied to each region of memory. When memory is accessed using segmentation, the segment table must be consulted to determine whether or not the access is legal. In this example, a process requests access to memory using a logical address. Since we do not have paging with this system, this logical address is not translated by a page table mechanism. However, this logical address is divided into a segment address and an offset into the segment in a manner similar to page translation. The MMU checks the segment table to determine if a particular memory access is valid. In this example, the segment table stores up to 4 permissions and up to 3 bits, a valid-invalid bit, a read-write bit, and an execute bit. In practice, most systems that support segmentation without paging normally only use 2 bits, valid-invalid and read-write. If the process tries to read from a segment that is marked valid, the memory access is permitted and occurs normally. The same thing happens if a process tries to write to a memory location that is marked both valid and writable. However, if a process tries to write to a segment marked read-only, or if a process tries to access an invalid segment, the CPU triggers a segmentation fault and the process is terminated. For some invalid accesses on a Unix-like system, this segmentation fault may be reported as a bus error. With paging systems, which comprise the majority of modern systems, including mobile devices, memory protection is accomplished by adding permission bits to the page table entries. In general, page table entries will have a valid-invalid bit and a read-write bit. The valid-invalid bit is used in the same way as it is for segmentation. Pages that a process is allowed to access are marked valid. Other pages, and any non-existent pages, are marked invalid. If a process attempts to access an invalid page, a CPU fault is raised, which functions like an interrupt to trap into the kernel. A Linux kernel will send a SIG-SEG-V or SIG-bus signal to the process, depending on the location in memory the process tried to access. In practice, this signal is normally not caught, and the process terminates. For historical reasons, this event is called a segmentation fault, or SEG fault for short. The read-write bit used to mark the text segment of a process, can be used to allow pages of memory to be shared between processes. Pages that are reentrant, or read-only, can be accessed by multiple instances of multiple programs simultaneously. This capability is useful on modern systems since multiple instances of programs are typically run at the same time. In the case of a web browser, for example, it is only necessary to load one copy of the browser program code into memory. Several copies of the browser can be run as several different processes, sharing the program code and thus saving memory. The open-source Chromium browser and its Google Chrome derivative allow each tab to run in a separate process. Shared memory pages allow the code for the browser, any extensions, and any plugins to be loaded only once, saving memory. This diagram illustrates how two processes can share a single page in RAM. Each process sees a handful of valid frames, one of which is marked read-only. If this memory frame contains code or other information that can be shared between the processes, then the two frame numbers will be identical within the separate processes. Each process may use a different page number to represent this memory location, however, since each process has its own independent, logical view of memory. Incidentally, this diagram is a conceptual diagram only. It does not directly map to any particular data structure in the operating system. Instead, the two tables illustrate how each process might see the page table. Newer AMD and Intel CPUs support an additional permission bit for setting execute permissions. This bit, called the NoExecute or NX bit, is actually an inverted permission. It is set to 1 whenever execution of data found on a memory page is forbidden. Originally, the NX bit was implemented by AMD on its 64-bit capable processors, using the marketing name of Enhanced Virus Protection. Intel followed suit and added this mechanism as the Execute Disable or XD bit. The concept behind the bit was to provide a mechanism that could be used to prevent execution of native machine instructions from memory space used for regular data. Although the primary beneficiary of this feature was a certain virus-prone system that is not a Unix variant, the Linux kernel does support the NX bit as a guard against buffer overflow and similar exploits. In the example presented in the hypothetical page table here, only the page with hex numbers 04A4 allows code execution. In the event of an exploit attempt, a malicious application could try to load code in another page, perhaps 04A1. However, since the NX bit is set on that page, any attempt to execute the code loaded by the exploit will trigger a CPU fault, and the process will be terminated. This mechanism increases the security of the system against certain types of attacks.